All right, so let's talk a little bit more about this RSS, or the residual sum of squares. So RSS stands for residual sum of squares, and you can write it like this. It's the residual, so the residual I'm writing as E transpose E. I'm writing it as an E because sometimes in my notation I've used an epsilon, and really I should probably use an epsilon hat or some other letter. And so I've chosen E here kind of for consistency, and I'm going to keep that throughout the class. But basically E is just a vector of the residuals. And so it turns out we can write this as Y transpose I, the identity matrix, minus H, the hat matrix, times Y. So I guess I just said this, but what is H? Well, it's that hat matrix. It's the matrix that puts the hat on Y. It's X times X transpose X inverse, X transpose. So what I want you to do is I want you to show that this is true. So I want you to show that the residual E transpose E is equal to Y transpose times the identity minus H times Y. So go ahead and work on this in your application exercise. Spend a couple minutes showing that this is the case. All right. So in the lab, I told you that you can estimate that sigma hat squared, or that variance of the residuals. I said we can estimate that using the residuals transpose times the residuals divided by n minus p plus 1, where p is the number of predictors in your model. So in the lab, we had 2 predictors, and then the plus 1 is because we have an intercept, and so we would divide by n minus 3 in that case. So we would be dividing this residual sum of squares divided by n minus p plus 1. So why is this the case? So let's go through a couple matrix facts here to work our way up to this. But the trace, so matrices have something known as the trace, and the trace of a square matrix can be written as the trace of A, and it's the sum of the diagonal elements. And so here are some facts about the trace. The trace of A plus B, if these are 2 matrices, A and B, is equal to the trace of A plus the trace of B, so that you can use this transitive, this property where you can basically pull that trace through. The trace of some constant C times the matrix A is equal to C times the trace of A, so you can pull a constant out like this. And the trace of ABC is equal to the trace of BCA is equal to the trace of CAB. So basically you've got this, this ability to sort of circulate, you can circulate matrices like this when you're taking the trace. So the trace is the sum of the diagonal elements. And here's an expectation fact that goes along with these trace facts. And if you'd like, you can try to prove this, but we're going to take it as fact here. So the expectation, so if you have X transpose times C times X, the expectation of this, X transpose CX, is equal to the expectation of X transpose times C times the expectation of X plus the trace of C times the variance of X. I'm going to say that one more time. So the expectation of X transpose C times X, where C is a constant and X is random, is the expectation of X transpose times C, that constant, times the expectation of X plus the trace of C times the variance of X. Okay, so we're going to use that fact here. And so notice I'm asking you to take the expectation of the residual sum of squares, and we've set this equal to the expectation of Y transpose, the identity matrix minus the hat matrix times Y, because before we showed that the residual sum of squares is equal to this. And you'll notice that this formulation is the same as this matrix fact here, where we have random. So we've got Y here is random on either side. And this part in the middle, I minus H, is a constant. Maybe we can remind ourselves about why H, what the components of H are and why that's a constant. So go ahead and calculate this expectation using that fact that I had given on the previous slide. I'm going to give you a couple minutes to work on that. That the expectation of that residual sum of squares is equal to sigma squared times n minus p plus 1. So make sure you show all of those steps in your application exercise. And that should make it pretty clear as to how we're getting this estimate for sigma squared, so that's sigma hat squared. Because we can just swing over this n minus p plus 1 to this side of the equation, and we're left with just sigma squared on the other side. And so we have the residual sum of squares divided by n minus p plus 1 is equal to our estimate for the variance. And so what is this n minus p plus 1? Well, that's just the degrees of freedom of our model. So this should ring a bell maybe from previous classes that you've taken. But in the lab that we were working on, we had two predictors. So p was 2, so p plus 1 was 3. And so our degrees of freedom for that model was n minus 3. So our estimate of sigma hat squared then is going to be the residual sum of squares divided by n minus 3. And then, of course, we can also estimate the standard error of a beta coefficient. So we did that in the lab by basically taking the square root of the diagonal of that variance matrix for beta. And so that will give you the individual standard errors for each of those beta coefficients.